Quantum physics is not just about tiny particles moving in the void. It also studies how these particles and other more widespread excitations can be exchanged, merged, or interwoven into a material. This behavior, known as quantum statistics, determines basic properties, as if something can condense or if it maintains a complex internal structure. If you like content, do not forget to subscribe to the channel and like the video, so you can be aware of more fascinating research on quantum physics and other scientific topics. Your support is fundamental to continue creating quality content. The work we analyzed proposes a general framework for calculating statistics in discrete networks. The authors developed a universal method for determining the generalized statistics of abelian excitements in networks of arbitrary dimension, unifying particles, loops, and objects of greater dimension. In quantum mechanics, exchanging two identical particles can change the sign and wave function, distinguishing between bosons and fermions. In higher spatial dimensions, anyons appear, whose interactions are key to understanding phenomena such as fractional Hall state and quantum computing. In 3 dimensions or more, there are not only point particles. Extended excitations such as closed loops or surfaces may also appear. The article highlights that statistics of these excitations are still in development, indicating the lack of a systematic framework to analyze them all. The challenge is that in a discrete network, each operator that moves an excitation can introduce phases dependent on local conventions. Distinguishing between artifacts and intrinsic physical properties requires a carefully designed procedure to avoid confusion. The authors introduce statistical processes that transform excitation configurations and return them to their initial state. By going through this closed circuit, the system acquires a collective Berry phase, which encodes the statistics of excitation. It is crucial that local phases are automatically canceled to avoid ambiguities. The article explains how a sequence of local operators is constructed, whose Berry phase encodes the desired statistical invariant, generating discrete results that do not depend on arbitrary network details. One of the most profound consequences of the work is the reinterpretation of the invariant phases as anomalies of type 't Hooft. These anomalies represent obstructions to convert global symmetries into local symmetry, connecting microscopic statistics with the global structure of the energy spectrum. The proposed framework not only identifies invariants, but also classifies statistics into finite abelian groups. This implies that the possible phases are quantified and related to the co-approval of mathematical spaces associated with higher-order symmetries. Finally, the message is that certain forms of quantum complexity are inevitable and cannot be eliminated without breaking symmetry. Generalized statistics act as a topological seal that prevents reducing the state to something trivial, showing the importance of geometry in quantum physics.